So I'm going to assume that most of you have probably never heard of Gen3D, which is very understandable, seeing as we're quite a new company. So I'll give you a little bit of a background. All of us in the company come from the academic world. So we were doing research at the University of Bath, and we were looking specifically in design and manufacturing with a focus on design for additive manufacturing or 3D printing, and looking at manufacturability and also generative design. And we did a lot of work and research with industry trying to identify the challenges of design for additive, which led us to create a geometry generation engine that creates manufacturable geometry based on a set of design constraints and manufacturing constraints. So, there we go. There we go. So this nature-inspired algorithm can create manufacturable geometry by simulating the manufacturing process as it designs. Now, what you have to do is basically put in your manufacturing constraints, and the more you can define them and the better they are associated with your manufacturing process, the more likely it is for whatever gets generated to be successful when you build it. And this can scale to any number of manufacturing constraints. And we started by looking at structural components, which is all great, and there's a lot of tools out there at the moment, topology optimization, and a lot of the generative tools out there are looking specifically at structural. But actually speaking to industry, we found that there's a lack of tools available to look at sort of fluid flow applications, and there's a lot of applications that's possible for additive with fluid flow. And so what we did is we created this software to import geometry and specifically flow paths, and then wrap manufacturable geometry around those and optimize designs. But the problem is that, again, speaking to some of the people we were working with, is that actually designing the flow paths itself is the thing that's very time-consuming. And coming up with more complex designs and very complex manifolds, conformal cooling channels, heat exchangers with lots and lots of elements and flows is all really, really time-consuming, and it's not very flexible, as well as coming up with different concepts and very quickly trying to explore the design space. So the other problem is that when it comes to the cost of your designs and the parts, 70% of the costs get locked in at the conceptual design stage. So it would be really, really beneficial to efficiently explore these early conceptual designs and try and come up with the optimal design. Now, because of all of this, we've designed our software to be as flexible as possible, track a lot of the concepts that you've generated, be able to compare them, as well as still adhering to a lot of manufacturability rules. So we're finally at the point where we're happy to sort of reveal what we've been up to. It's still in the beta stage at the moment, but I'm going to go through and show you a demo of a test case that we designed, which is a rocket nozzle with conformal cooling channels in it, which just gives you a flavor of what you can potentially do with our software. Now, to start with, you can import geometry that you've designed in a CAD tool. In our case, it's the actual bodies of the shell of the nozzle. You can also have some primitives in there, or you can just design flow paths if that's what you want to do. Everything is meant to be draggable and clickable and just sort of unconstrained, so it's very easy to move things around. And it's all with reference to a build plate, so it's got the manufacturing in mind. Now, to start creating some flow paths, it's all node-based, so you can put nodes of a certain size or radius on the surface, or you can actually input the coordinates themselves if you want to be more specific. And so you can put it on the surface of a node, you can drag that around, and then all you have to do to create the first flow path is click on a node, press connect, click on the other node, and you instantly get the spline. But then you can start moving the vectors around, you can move the positions, so it's all live updated and very easy to sort of start positioning things. You can further fine-tune things by putting in a mid-node, by just as you just saw. And then you can sort of fine-tune and further place the positions of the nodes. You can also edit the weightings of the different flows so that you can, again, in this case, try and get it sort of conformal to the body of the nozzle. We're currently working on a tool to automatically create conformal flows to bodies, but for helical flow paths, we can actually do conformal channels, which I'll show you right now. So if you want to create a helical toolpath, again, you start node, and then you need an axis to rotate around. So as you see, we'll create an axis in the middle of the channel. And then you select the start node, select the axis, and you start with a ring, and then you can specify the height of it or the number of revolutions. You can also then place the start or end node on any of the surfaces, and it will automatically update, and you can even just drag it as well, and it would update live. You can then conform that to the body of the nozzle, just by selecting the model, and it will conform to it. You can then set an offset, so you want that inside or you want that outside of the body. And as it designs the rest of the helices, the colors of the flow paths just indicate certain parameters. So pink is that it's going to be overhanging, and that the cross-section of those flows are going to be compensated to be self-supporting, so they turn into a teardrop shape later on. Green is too much curvature, so you can set a limit on that if you don't want certain pressure drops in your flows. And red will be intersecting geometries. You can also create a ring by just specifying a helix and then not having a height, obviously, on that. You can hide, and you can make transparent models so you can see what's going on the inside. And that's, at that point, I'll give it a second. Yeah, so it's still just fine-tuning stuff. But the next thing we want to do is in the combustion chamber, we want to have the fuel flow going on to the inside. So what we're going to do is create an area for the fuel to be injected into the combustion chamber. Again, just put 2 nodes in and connect them up. You can invert the vectors in case it's got the opposite direction. Again, you can just drag that into as far as you want into the combustion chamber. And then what I'm going to put in now is a void space, or an area where we don't want any material. So obviously we want the fuel to go in. So we're going to put a little cylinder in the way. So that's one of the primitives that we've got. You can scale that or dimension it if you want, and just place it right in front of the nozzle. And then what we're going to do is pattern that. So you can select the bodies you want to pattern, and then you're going to select the axis, and then you get a live update of the pattern. You can set how many patterns you want. You can set the angle for it. You can do a rectangular pattern if you want. And then you just set that in, and it locks it. But you can also live update the pattern before you've set it, so you can actually fine-tune it on the go. You can constrain nodes to models. So you can then select a node to constrain to the body, which means that if you move that model around, that's then going to be locked to that body. So you can then start playing around with positioning and trying to sort of pack all your components together. And then when you've done that, so we're going to define all of the bodies that we imported as solids, so that we will create geometry for them. And then at that point, if you're happy with the concept, you can go and generate the actual geometry around all of that. It's always a good idea to save it. And so you click on generate, you choose what sort of resolution you want. So we've got coarse, medium, and fine, or custom. And it takes about 10 seconds to solve for a coarse, and up to about 3-4 minutes for the fine. And it is a voxel-based solver. So again, that resolution is then the voxel size. We've done up to like about 150 micron voxel size. Once it's generated, you can slice the model and have a look and see if everything's been generated the way you want. You can look at how those flow paths have been compensated for any sort of overhanging geometries. And if you're happy with that, you can then export the smooth model and go for it. Or our latest feature that's literally being worked on at the moment is to try and explore the designs. So every time you hit generate, we save a sort of snapshot of that design at that moment. And you can go through and look at the various metrics for all the designs that you've generated. So you can move things around. You can really start exploring, different options, having different number of patterns or different cross sections, and get a thumbnail of each one that you've done if you want to look at some in more detail. And you can look at the various metrics going down. And then, once you've sort of found the concept that you had, because it might not be the current one, it might be one that you did way, way back, then you want to load that one back into the environment, and you're happy with it, so you say, okay, that's the one we want to go for. It just loads it back in, and you can continue from where you left off and even make some more adjustments again. So this wasn't the one that we ended up going with, but the one we ended up going with was this one, which had vertical helical paths. And that's sort of what gets exported from, a bit of noise. And that gets exported as a nice smooth solid, and you can send it to the printer, and then you can go and test it. Turn the volume off. Cheers. And then you can go and test your part, see how it performs. And if you're happy with it, then you can go on and print it in whatever material you wanted to print it in, or in plastic if you wanted to. But basically, that's a sort of quick overview of what we've got so far. It's still in the beta stage, so we're testing it with certain companies, so it's a closed beta. We're looking to launch this in the sort of summertime. It's obviously going to be a small-scale launch, and depending on how things go, we'll scale up from there. But hopefully you've seen how potentially people could have a flexible sort of environment to explore designs in, as well as always adhering to the manufacturability of the design. And if you want to see more, you want to see a live demo, we're in the booth 68, and you can have a little play around with it yourself. You can go on the website and see more, or you can just fire us an email and get in touch if you want to even try it out yourself, and we can figure out how to get it over to you. But thank you very much.